Today, we are going to see the orthogonal transformation and reduction of quadratic form into canonical form using orthogonal transformation. We will see the problem based on the reduction of quadratic form. So, the first problem, reduce the quadratic form to a canonical form by an orthogonal transformation that is 2x1 x2 now plus 2x2 x3 minus 2x2 x3. Also find the nature rank index and signature of the quadratic. Solution. First we have to write the given quadratic form in matrix form. First we have to write the given quadratic form in matrix form. That is 2x1 x2 minus 2x plus 2x2 x3 minus 2x3 x4. So x2 2x1 x2 plus 2x1 x3 minus 2x2 x3. So the matrix form is coefficient x1 square of coefficient of x1 x2 of coefficient of x1 x3 of coefficient of x1 x2 coefficient of x2 square of coefficient of x2 x3 of coefficient of x1, x3 of coefficient of x2, x3 and coefficient of x3 square. So using this, we get the matrix as is equal to 0, no x1 square, so 0, so half of x1, x2 is 1, and half of x1, x3 is 1, and then half of x1, x2 is 1, 0, and x2, x3 is minus 1, and then half of x1, x3 is 1, and then half of x2, x3 is minus 1, 0. So this is your matrix. Now, next, we have to do orthogonal transformation. Transformation for the symmetric matrix E. First, we find the characteristic equation. The characteristic equation that is lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. Here s1 is equal to 0, s2 is equal to minus 3, and s3 is equal to minus 2. The characteristic equation is lambda cube minus 3 lambda plus 2 is equal to 0. Next, eigenvalues. Eigenvalues are the roots, the characteristic polynomial that is 1, 1 and minus 2. 1, 1 and minus 2. Next, we have to find the eigenvectors or the corresponding eigenvalues. First, eigenvector for lambda is equal to 1, that is 1, 1, 1, 1, 1, minus 1, 1, minus 1, 1, lambda is equal to, so we'll get a minus lambda is, so minus 1, minus 1, minus 1 of x1, x2, x3 is equal to 0, 0, 0. So the equations are minus x1 plus x2 plus x3 is equal to 0. x1 minus x2 minus x3 is equal to 0. x1 minus x2 minus x3 is equal to 0. Here all the three equations are same. Same equation. So eigenvectors are put x1 is equal to k1 and x2 is equal to k2 or any real numbers. Then x3 is x3 is equal to k1 minus k2. So x1, x2, x3 is equal to k1, k2, k1 minus k2, which is equal to k1 times of 1, 0, 1 plus k2 times of 0, 1 minus 1. Next we'll find the eigenvector. Eigenvector for lambda is equal to minus 2 a minus 2 I of x is equal to 0. So that is lambda is equal to minus 2. So minus of minus 2 will be 2, 1, 1, 1, 2, minus 1, 1, minus 1, 2 of x1, x2, x3 is equal to 0, 0, 0. So we get the equation 2x1 plus x2 plus x3 is equal to 0. x1 plus 2x2 minus x3 is equal to 0. x1 minus x2 plus 2x3 is equal to 0. By using cross multiplication method we get we take the equation 1, 2, 1 minus 1, 2, 1, 1, 2. So x1 divided by minus 1 minus 2 is equal to x2 divided by 1 plus 2 is equal to x3 divided by 2 minus 1 is equal to k. So x1 by minus 3 equal to x2 by 3 equal to x3 by 3 is equal to k. So we get x1, x2, x3 is equal to minus 3k, 3k, 3k. So which is equal if you only can take the 3k common out, so we'll get minus 1, 1 and 1. So the eigenvectors are eigenvectors are 101, 1 minus 1, 1 0 1 0 1 minus 1 and minus 1 1 1. So this eigenvector came from lambda is equal to 1 and this will came from lambda is equal to minus 2. So we know that on a symmetric matrix, we know that on a symmetric matrix, eigenvectors came from the distinct eigenvalues eigenvalue or orthogonal. Therefore, therefore, you can take this as x1, x2, x3, x1, x3, and x2, x3 are orthogonal, but x1, x2 need not be orthogonal, but x1, x2 is not orthogonal, but but we need orthogonal vectors for orthogonal transformation. So take any two vectors. So here I am taking x1 and x3. Take any two vectors here. I am taking x1 and x3. One zero one minus one one and one. The third vector I can take it as A, B, and C. The condition that x3 is perpendicular to x1 and x3 is perpendicular to x2. We find x3, that is a plus 0b plus c is equal to 0 minus a plus b plus c is equal to 0. So again using cross multiplication, again using cross multiplication method, we get 0 1 1 1 1 minus 1 0 1. So a by 0 minus 1 equal to b divided by minus 1 equal to c divided by 1 minus 0 is equal to k. So a by minus 1 equal to b by minus 2 equal to c by 1 equal to k. We get a b c is equal to minus 1 minus 2 1 k. So the three mutually perpendicular vectors are 1 0 1 minus 1 1 1 minus 1 minus 2 1. Okay, next we have to normalize the vectors. Normalized vectors are 1 by root 2 0 1 by root 2 minus 1 by root 3 1 by root 3 1 by root 3 minus 1 by root 6 minus 2 by root 6 1 by root 6. So now we can able to write orthogonal transformation matrix, that is the model matrix N. The model or orthogonal transformation matrix N is equal to 1 by root 2 0 1 by root 2 minus 1 by root 3 1 by root 3 1 by root 3 minus 1 by root 6 minus 2 by root 6 1 by root 6. So also N transpose A N will be is equal to 1 0 0 0. It came from a second eigenvalue, so 0 minus 2 0 0 0 1. Since this came from lambda is equal to 1, sorry, lambda is equal to 1, and this came from lambda is equal to minus 2, and third one will be automatically lambda is equal to, and the canonical form is form y1, y2, y3, the matrix 1, 0, 0, 0, minus 2, 0, 0, 0, 1 with y1, y2, y3, so it is equal to y1 square minus 2 y2 square plus y3 square. So this is your canonical form, or reduction form, or reduced canonical form. Next, we'll find the rank, signature, index, and nature. The eigenvalues are eigenvalues are 1, 1, minus 2. Here, eigenvalues are both positive and negative. Therefore, nature is indefinite. Number of non-zero eigenvalues are 3. Therefore, rank is 3. Number of positive eigenvalue is 2. Therefore, index is 2. The difference between the number of positive and negative eigenvalue is 2 minus 1, which is 1. Therefore, signature is 1.